We stated in the introduction that we built this course with the intention of helping people with little or no background in image processing or computer vision break into object detection and deploy state-of-the-art object detection solutions. That said, let's start by understanding how images are formed. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. We shall consider this image in its grayscale and colored version. Look at the black and white image. That is this grayscale image right here. Let's try to zoom, and we have this. It can be observed that each and every box which makes up this image takes up a color between black and white, passing through different shades of gray. Now, when we just spoke of box, what we mean by this is when you try to zoom this, let's take this off and zoom this. You see we have this image, and then we have these boxes which all make up the image. So you have this box here. You see, you cannot go further because you have just this box and all the other boxes which make up our full image. And so, as we just said, each and every one of this box takes up a value between, or takes up a color between 0 and white, passing through different shades of gray, hence the term grayscale image. Let's zoom again, and then let's get to this parts where we have more darker colors. So you see, when we zoom, we see you have this great view of all these different boxes. You see, we go from, let's say we have this kind of light gray to this dark gray. So this is actually what makes up an image. Now, these boxes are known as pixels. So each and every one of this box is a pixel, and the pixel is the most basic component of an image. Each pixel, as you can see here, depending on how white or dark the image is, will take up a value between 0 and 1. 0 to 1 is like going from black to white. Reason being that a completely black pixel will take up a value of 0, and a completely white pixel will take a value of 1. And so these pixels, or these dark gray pixels, like this pixel and this pixel and this pixel, will have values closer to 0 as compared to this light pixels here. So this pixel here will have a value closer to 1 instead. And so here we could have a value like, say, 0.8, and then here you could have a value like, say, 0.1. Another way we could look at this is, instead of going from 0 to 1, let's take the 0 and 1 off. Instead of going from 0 to 1, we could go from 0 to 255. Let's have this back. So here we would have 0 for the dark or a completely dark pixel, and 255 for a white pixel. And the values will span across this range. Since this is light gray, you would have a value like, say, let's take a value like 230. While with this, you would have a value like, let's pick this pixel here, you would have a value like say 10. So that's how we look at this. So you could go from 0 to 1, that is, you could make sure each and every pixel takes a value from between 0 and 1, as well as you could make sure all the values taken up lie between 0 and 255. In order to better understand this, let's take up this example from Sedesa.io site. Here we see this image here. You have this image right here, and then you have the values for each and every pixel which makes up this image. Notice how when you zoom this image, what you get is this image which looks more like a human face. And so let's fix at this point. You look to the left, you have a value of 255, meaning that we have a purely white pixel right here. Now let's get to this here. The value you get is 20. So you see that the value obtained is closer to 0 as compared to this purely white pixel here. Another thing we want to notice is the fact that this initial image right here has now been converted into a matrix. So if you're new to linear algebra or you don't have any math background, this shouldn't be a problem. Basically, this matrix contains all these different pixels. So it's kind of like a representation of this image. And so here we have this matrix. Generally matrices are noted like this. So if you want to have a let's say 2 by 2 matrix, you would have a matrix like this. You have that, you have a value, say 1. No, let's take values between 0 and 255. So let's say 10, and then you have 100, and then you have 210, and then you have 11. So this is what we call a 2 by 2 matrix, because we have 2 values in this x-axis, or in the horizontal direction we have 2 values. You see, if you count them from the horizontal direction, you have 1, and then you have 2. And if you count in the vertical direction, you have again 1, and then you have 2. Hence 2 by 2 matrix, meaning we have 2 times 2 is actually 4. So 2 by 2 doesn't mean 2 times 2, but when you calculate 2 times 2, you have 4. Now we've seen this. What if we get back to our image right here? If we try to count those pixels, we would have a value of 32. And so here we have 32 pixels in the horizontal direction, and then we could also count for the vertical direction. And this also gives us a value of 32. So you guessed that right. We have now a 32 by 32 matrix. So this image we have here is 32 by 32. We have a width of 32 and then a height of 32. And so here, multiplying 32 by 32, we have a value of 1024, meaning that we have 1024 different pixels which all form this image. At this point, we're ready to dive into looking at colored images. And we're gonna make use of Pine tools to understand how color images are stored. As you could see here, we have this image, and then we have 3 different components. So unlike with the grayscale where we had for each pixel, we had just a single value, here instead for each pixel, we are gonna have 3 different values. And all these 3 different values will represent the 3 different channels we have, which make up the colored image. So here you'll notice that we were trying to decompose this image into its different channels. So each pixel, as we said, has 3 different channels, and then we could decompose this here. You see we have this output right here. Notice that we have just this output, this blank output, because we haven't selected any of the options. So we select the red and we decompose, and guess what we have? We have this image where we're leaving from either a completely red pixel to a completely dark pixel. So let's have this here and take this off. Okay, we're leaving from either this completely red to this completely dark, or from this completely dark to this completely red pixel. And so as you could see here, unlike with a grayscale where we're moving from white to black, or let's say we're moving from black to white, here we're moving from black to red. And then the value, or the values for each pixel, range between 0 and 255, still as we had seen with the grayscale. So we have this same value range, but the difference here is we're going from black up to red. And so if a pixel is completely red, then it'll take up a value of 255 for the red channel. And then if it is completely black, like with this one, it takes up the value of 0, still for the red channel. Now let's go ahead and then work with the green channel. Let's take this off, and then we have the green channel. So here we have this green channel. Let's decompose and see what we have. As you can see here, we have this green channel. Again, the values range from 0 to 255. We're going from from black to green. And then we have this value, yeah, 0 to 255. And that's it. Let's go to the next. We look at the blue, and then we decompose. You see, we go from black to blue. Now, if we take all these 3 combined, you would have our initial color. So this is to say that this image has now been broken down into this red, green, and blue components. And this representation of an image into its RGB components, that is RGB channels, is known as the RGB color space. Another important point to note here is we had this grayscale image which was represented by a matrix where we have a certain number of pixels in the horizontal direction and a certain number of pixels in the vertical direction, and each of these positions are occupied by the pixel values. So we have something like this, which we saw already. Now, getting into the color images, we do not have just one matrix like this. Since each pixel is represented by 3 numbers, we have a combination of 3 different matrices. And so if we suppose that for this grayscale where we had this matrix, we consider that this matrix is 1 dimension, then this colored image, you guessed it right, is 3-dimensional because it's made of 3 different matrices. Each matrix shows how this image varies throughout in each of the channels. That's for the red, we see these variations, and these variations. So here we have this 3-dimensional image, 1, 2, 3-dimensional, instead of this 1-dimensional image, which is the grayscale. Note that the width and the heights are maintained. So if, let's say for example, this is let's say this is 20 by 30. So if this is 20 by 30, then this is a matrix 20 by 30. Here we have 20 by 30 still. So the height and the width do not change. But then since we have 3 dimensions, we're just gonna add this here. So we have 20 by 30 by 3, unlike here where we have 20 by 30. We now understand how computers store images. But before moving on, it's important to highlight this amazing library of OpenCV, which has been used by millions of engineers around the world in image processing and computer vision. Getting back to Google Colab, we're going to drag this image in place right here under this folders. So here we have this color spaces. Let's modify this. Let's rename this and say initial image. Okay, so we have this initial image right here, and then the way we work with OpenCV is very simple. We'll start by importing OpenCV because on Colab this has already been installed. So all you need to do is to import OpenCV. Now the way it's imported is actually CV2. So we have that, and then we run the cell. Once you run the cell, you could go ahead and read this image right here. And so all again we do is have our image here, so we call this image, and then we do cv2.imread, image read, and then we pass in this file name right here. We have the initial image.jpg, that's fine. And then from this point you could actually do an image write. So let's have this. Let's say output is equals cv2.imwrite, and then you choose output image. So let's have that. We could even change the format. So let's say .png. So we have this input, and then now we have this output. Let's run this, and we should have our response. You see, we get this error. The reason why we're getting this error is because we just specified the output file name, but we didn't specify the actual variable, which is this image here. So let's have this variable specified. We run this again, and that's fine. So let's refresh this, and you see we have this output image. You see, it should be the initial image we had, and we also have this initial image. There we go. So now what if we want to flip this image? So here we have flipped image, and then we have cv2.flip, and then we pass in our image, and then we pass in 0. Now we'll understand why we pass in 0 shortly, but let's check this out here in the OpenCV documentation. So you could always feel free to get back to the documentation. There we go. We have here docs.opencv.org. Let's search flip, and normally you should just click on this here. Search that already. Okay, so we have that flip. So here we have the definition of this method, so you shouldn't have problems working with OpenCV. Now let's get back to this. The aim here is not to explain OpenCV, but to tell you that you would generally be working with OpenCV when it comes to image processing, and so you have to get used to this very amazing library. So there we go. We have this output, and then we modify this image. Is now the flipped image, and let's run this cell. Okay, that's fine. So we run this cell. The way we run this is actually you could click on this to run the cell, or you could press Shift Enter. So that's it. Now we get back to this, we refresh this, we have our initial image, which was this image, and then let's look at the output image. you notice that this output we obtain has been flipped. So that's how powerful OpenCV is. You see, with just this line of code, a single line of code, we're able to flip this image very conveniently. You should note that each and every time we are going to use the OpenCV library in this course, we are going to explain it in detail such that anyone could understand. We are now going to get started with understanding how object detection algorithms work. We've seen already that the output of an object detection algorithm will be like this. So we have this original image right here, and then what we get as output is something like this, where we detect a face, we detect the face here, we detect a dress, we detect a dress, and we detect this bangle. And the way these algorithms work in general is in two major steps. The very first step is feature extraction, and then the next step is applying machine learning to be able to predict whether the extracted features match with the features which are common to a particular object. Let's explain. Machine learning is a field of computer science in which we do not teach a machine how to act like humans would usually do by giving this machine explicit information. Instead, what we do is we are going to tell the machine that this is an image and this image contains a person's face. This is another image and this image contains these two faces. This is an image and this image contains this face. So we're going to have, for example, let's say we're going to have 1 million of such faces. So we have 1 million of such faces, hence the 3 dots. We go from 1 to up to the 1 millionth face. And so when the machine sees all these different examples, it actually learns to get an image as an input and know that there is this face right here. And now once it is given this image, so once we pass this image into our machine learning algorithm, because it has learned to correctly detect a face, it now is able to detect that there's a face at this position on the image. But to ease the task of this machine learning algorithm, we need this feature extraction unit or this feature extractor. Let's get the point, like let's understand what feature extraction is all about. Here, let's take this off. We have this person's face. So we've seen this person's face right here. And now what a feature extractor will do will be to get relevant information from this image. And so if you're detecting a face, you would want to have this kind of information as output. So we would have this kind of information as the output of this feature extraction unit. And so what the machine is going to learn from isn't the image itself, but this extracted features in which we've removed all unnecessary information from. With that, getting back to this set of 1 million images, what the machine will be taking as inputs will be this person's face. You have this, and this other features right here. This machine learning algorithm is going to learn how to see, for example, this feature and be able to detect correctly that this contains a face. And this is because human faces, let's take the example of the case where we're dealing with human faces. Human faces have certain characteristics, like obviously you would have a person with 2 eyes, a nose, and a mouth. And because we have this recurrent characteristics, the machine will be able to learn from all this large data to be able now to say whether from this we are having a face or not. And in the case of object detection, to be able to locate the exact position where this face is found in the whole image. The very first object detection algorithm we'll be looking at will be the Vowel and Jones algorithm. This paper was published in 2001 and is entitled Rapid Object Detection Using a Boosted Cascade of Simple Features. And here are the features in question. Before moving on, we should note that this algorithm was developed for grayscale images. And scrolling down, we could see how these features have been applied on the image. It should also be noted that this Vowel and Jones algorithm is a classical computer vision algorithm, where, as we can see, this algorithm makes use of the fact that the eye region, that's this region's here, is generally darker than this nose region. So what do you observe here from the way these features were applied on the image? You'll observe that we have this white here, and then we have this dark sections, and so this actually matches up with a person's face. And then the other way they applied these features in this paper, or this other feature which we could apply, which is this one, is where you have, or where you notice the fact that generally this region should be darker than this region just below it. So if you have this region here, you should have this one to be lighter than this region up. So this is how this feature here is used in extracting useful information from our image. And once these features have been passed around the image, that's slided through the whole image, we'll then have enough information to train our machine learning algorithm. And so let's take an example where instead of a human face, we are given this image containing a car. You would find that we are going to take this features which we've defined already, or which were defined in the Vowel and Jones paper, and then we'll pass it, or we'll slide it through this whole image. So let's say we have this here. Let's take this feature. Here we had a dark region, and then here we had dark region. So when we pass this feature here, you see that it wouldn't match, because in this image actually here you have instead a dark region, and here you have a lighter, and here a lighter region, and so this wouldn't match. And so this will continue sliding. We'll go to the next. We'll have something like this. So we actually trying to extract useful information. So we have this. We expect to have something dark here, something dark here, but we don't get that. So we keep on moving. So you find that we'll move on, or we move throughout this whole image, and maybe in some cases you would have this matches, but the way this matches will be wouldn't be similar to the way this matching is done for a human face. And so if you're dealing with this feature right here, which we've seen already, where we have the light in the middle, and then we have the dark region, and we pass it on all these different faces here, you would find that this will generally match at the top region of the image. So you generally have this kind of match at this top region, because this is actually a face image. Now for the car, you may have that match at certain positions, but it wouldn't be in the same way this matches up with human faces. So you could go on and you see that it's always kind of similar kind of scenario. You have this always. Now you may have this human smiling. So here you have, let's check out the other features here before moving on. We have this other feature right here. Let's have that. We have this feature right here, and then getting back to the images, you'll find that for men who generally have mustaches, you'd have something like this. So we have this mustache region which is dark, and then we have this lip region which is light. Oh, sorry about that. Let's go back and have this. So we have this region is dark, and then we have this lower region which is light, and which matches up with the feature which was given in the paper. So let's have that. It matches up with this feature. So you find that if you get to this one too, you see you have something similar. You have a dark region at the top and a light region at the bottom. And with this, we've seen globally how this Vowel and Jones algorithm, or this Vowel and Jones breakthrough algorithm, actually works. If you want to get all the details, you could check out this paper. Depending on how much experience you already have in computer vision or mathematics, you would be able to understand how all this works in detail. But for this course, we'll just focus on explaining in a high level manner how this works. The next algorithm we'll be looking at after the Vowel and Jones algorithm is a histogram of oriented gradients algorithm. We're getting this from Learn OpenCV website. So here, as usual, we're gonna have a feature extractor and then a machine learning algorithm making use of the extracted features to say whether at a particular position we have an image or not. So here they're taking this example of this patch. Recall how we did with the vowel and just algorithm, where we had this different patches. Like we actually slide through the image. We go this way, we slide and go this way, and so on and so forth. So we suppose that we've slided throughout, and then we've gotten to this position. At this position, they zoom this so you could see clearer. And then we have these arrows. You see some appear smaller, some appear medium, some appear longer, and so on and so forth. So we're gonna explain how or what all this actually mean. And then apart from this, we're gonna look at this gradient magnitude and this gradient direction, which actually happen to be the information we're extracting from this image right here. Now let's get straight into the matter. So here we're supposing that we have this, which has been like we are at this particular position, and then we can see this clearly from here. Now instead of having this image here, let's draw something similar just below. But here we take a simpler example. Let's take something simple. Let's have this, and then have this, and this. Okay, so let's suppose that at this position, so we're taking a pixel here. This isn't the whole image. This is a pixel, which is part of this patch which has been selected. This patch right here. So recall we sell pixels already. These are different pixels. And then if we had at this particular position, let's say we have a pixel value of 10. So pixel value of 10 means we're having a very dark pixel. So let's suppose that we have this pixel right here. So let's have this pixel alone. Let's say even 30, because it's not actually dark, it's brown. So let's say we're having something like say 50. So we have a value of 50 right here. And then around this value, or around this point here, we have this gray, light gray, light gray, light gray. We have brown, and so on and so forth. So let's suppose we are not going to take exactly what we see here. We just consider some values. So let's say we have 255. So suppose that here is purely white. Now from this here, the way we obtain this gradient magnitude is that for each position, we are going to say, okay, we're going to subtract this 2. So when we subtract this 2, we obtain an answer. 111 minus 49 is 62. So we have a value 62. So we subtracted this 2 here in this horizontal direction, and then we subtract this 2 in the vertical direction. 255 minus 146 is a value like 99. So here we'll have 62 and 99. And then to obtain this magnitude value, we'll take 62 squared. So we have 62 squared plus 99, sorry for this, it's 99 square, and then we'll get the square root. So you don't really need to get into understand why we're doing all of this. Just get the point, like try to understand what or why this algorithm makes sense when it comes to extracting these features from here. And so from here, if we calculate this, we should have a value of about 116. So here we have 116. So this means that this here will be replaced, or this value of 50 will be replaced by 116 to tell us that we have this magnitude value of 116. Now, what about the direction? To obtain the direction, we are going to take, like we had these two numbers, we're going to take the tan inverse of 99 divided by 62. So we get this value that gives us the angle actually. So you'll notice that these values here are ranging from 0 to 180. So generally we work from 0 to 180. So we'll get the angle and then we'll replace it right here. And so while for the gradient magnitude we have values like 196 which surpass 180, here we just have values ranging between 0 and 180. Now we've seen that with this here we've obtained the magnitude and now this angle. Now what does this, or how is this related to this plot we had here before? Now if you notice, we have this here, as we said already, this arrow looks longer than, say for example, this arrow. And now the reason why this arrow here looks longer than this arrow, or first of all, the reason why this arrow is actually this long is because this is its magnitude. So is this magnitude we just calculated right here. And then the Next one we could look at will be this one here. So let's take this example and you understand why this is long and then this is small. Now if we take this example, we have here this minus this, 40 minus 11, we have 29. So we have 29, and then next one, 50 minus 25, we have 25. Okay, so now we do 29 square plus 25 square, we get the answer, which is 38. So we have a magnitude of 38, and then we have an angle tan inverse of 25 divided by 29. Okay, so as I said already, you don't really need to get into understanding all the details. The point we're trying to make here is that because here we have these values, like if you notice, like if you pick out this pixel, you notice that these values are around the value 30. So here we have 11, 50, 40, 25. So it's just around the value 30. Whereas here we have this value 50, we have, it's true we have 49, but we have 146, we have 111, and we have 255. This means that at this position of this pixel is surrounded by other pixels whose values are quite different from its own value. And so this means that if this here is a dark pixel, then we're surrounded by light pixels. So if you look at this, let's pick out one. Let's suppose we have in, let's say, yeah, let's pick this one, which is long. No, this one is actually light, so let's take this one. So here we have in this dark picture, this dark pixel here. So if we take out this dark pixel, you notice that we're surrounded by this light. This is light, this is kind of light, this too is light, this too is light. Now if you take this pixel here, let's take this pixel here, and we understand why this is very small. This magnitude here is very small. If you look at this pixel, you see here we're surrounded, this is actually light, so we're surrounded by light, 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 and light. And so because there's no great difference between this pixel surrounding this pixel and the pixel itself, we would have a smaller magnitude, as we've seen here. We've seen here we had 38, smaller than, or way smaller than this 116. Now let's take another example so it becomes even more clearer. Supposing we have here 50, or we've picked a point. Let's say we pick this. No, let's just do it here. So we have 50, we have 50, we have say 49. So just to tell you that they're actually very dark pixels. 49, 49, and then here we have 50. You'll find that here we do 50 minus 50 will give us 0, and then 49 minus 49 will give us 0. So here we have a magnitude of 0. Obviously 0 square plus 0 square will give us 0. So we have a magnitude of 0. It's kind of telling us that this here is going to have no value. That's why you see, if you notice at this point here, at a certain point, you don't even actually have the arrow. Now let's increase this to 51, so we can have a value of 1. So we have 1 square plus 0, and this gives us 1. So we're gonna have a very small tiny arrow here. Now the angle 2 will be gotten in a similar way. So we have tan inverse of, or say 0 divided by 1. Tan inverse of 0 divided by 1 will give us an angle of 0. But if there's one point we have to note here, is the fact that this technique of extracting these features permits us to see directly the regions where we have pixels or pixel values which are quite different from each other. So if you look at this here, you'll notice that around this we have, you see, these magnitudes, very small magnitudes actually. And then as we get to this fourth row, 1, 2, 3, fourth row, as we get to the fourth row, we're going to see this here, 1, 2, 3, 4. We start having this higher magnitudes. Here we have this higher magnitudes, average magnitudes, higher magnitudes. So we start having this higher values around here because we have pixels which surround each other and then have quite different color values. And so with this, we've understood the logic behind feature extraction in the Haar algorithm. And then as we've seen, once we have this gradient magnitude, or this gradient direction and the gradient magnitude, we will create this histogram here. In this article, they explain in detail how this histogram was gotten. But here, the aim is to explain at a high level why we actually even doing the feature extraction and the logic behind the feature extraction. And to create this histogram we have right here, it's actually a 9-bin histogram, and each bin actually represents a particular gradient direction or a particular range of values for the gradient direction. So we're going from 0 to 180 degrees, and then here we have 0 to 20, 20 to 40, 40 to 60, and so on and so forth, up to 160 to 180. And so we're going to look at from 0 to 20, we get all the different values which fall under this range, that's 0 to 20. So for example, we take this value, we get its corresponding magnitude, which in this case is 165, and then we stack it up here on this bean. So if we had this bean which was initially like this, we now have 165 stacked up, and then we move to, let's say we take this other value 9, which lies between 0 and 20. We take its corresponding value 17, will be a smaller value, so we'll have something like this, because we're going from 0 to 100, and this actually is 65 here, 65. So 0 to 165, and then we're gonna add up 17, and then we take so that one, this is 11, take another small value, and so on and so forth. So basically all these values between 0 and 20 would have their magnitudes being stacked up to the final value we get. And so this is the final value we get here. And overall, what we notice is where we have the direction which has its magnitudes having very high values would have the corresponding high values here seen clearly on this histogram. Hence the term histogram of oriented gradients, which will then permit us to obtain some feature vectors. And then once we have those feature vectors, we'll then be able to apply machine learning. So with the Vowel and Jones algorithm, we had some set of predefined features which we've seen already. This is an example of one of those features. With the Haar algorithm, we have some feature vectors which are gotten from calculating the gradient magnitude and the gradient direction for each and every pixel. But one thing they have in common is the fact that after doing this or carrying out this feature extraction, we apply machine learning to say whether a particular object has been detected or not.